The metabolome is the complete set of low molecular weight metabolites in a living organism and is often regarded as the most phenotypically relevant information because it's furthest downstream in the central dogma. Linus Pauling referred to metabolic analysis as the wave of the future towards understanding human disease, and today metabolic profiling is being used to understand the molecular framework and homeostatic flux that underpins disease states. Additionally, metabolomics is utilized for drug validation and the discovery process of new biomarkers for personalized medicine. The future of metabolomics will serve to support existing omics-driven hypotheses, as well as reveal new information about disease states. A comparative study of omics publications was performed to determine the growth within each of the omics disciplines. The study revealed that although the total number of metabolomics papers is less than other omics disciplines, metabolomics is growing at a much faster rate. This accelerated growth is due to recent advancements in analytical instrumentation. The global market for metabolomics, which includes dollars spent on research, services, and instrumentation, is predicted to grow 5 times in 5 years. The market is currently estimated at $626 million and is expected to grow to over $3 billion by 2015, with the vast majority of business located in the US and Europe. Yuji Kano, president of Human Metabolome Technologies, was cited in a technology segment of Nature magazine that discussed capillary electrophoresis as an emerging technology that should be used in addition to conventional metabolic profiling technologies. In September of 2012, the NIH announced an initiative to accelerate growth in metabolomics and plans to invest over $51 million by 2017, or $14.3 million per year over the next 5 years. $9.1 million has been awarded to the Metabolomics Research Corps at the University of Michigan in a joint collaboration with Agilent Technologies and Human Metabolome Technologies. HMT will provide the know-how for the CMAS platform. Other ongoing collaborations include David Sabatini at the Whitehead Institute, Joan Brugge at Harvard Medical, and Thomas Seyfried at Boston College. In 2003, Human Metabolome Technologies was established as a Keio University spin-out venture from Dr. Tomoyoshi Soga's group, the pioneer in CEMS. Since then, HMT has optimized both global and targeted service packages for a broad range of research endeavors in the pharmaceutical, biotech, and food production industries. In Japan, HMT has formed alliances with Agilent Technologies, Chugai Pharma, Mitsubishi Pharma, and the Japan National Cancer Center. HMT is headquartered in the city of Soroka, located in the Yamagata Prefecture in the northwest region of Japan. Soroka is home to the largest CEMS metabolomics facility in the world, with over 50 instruments optimized for various samples and experiments. Business operations are located in Tokyo and Kyoto. HMT has recently expanded into the United States and selected to launch operations in Cambridge, Massachusetts, to better serve the global epicenter of biomedical research. In a typical CEMS system, the capillary electrophoresis component is connected to a mass spectrometer by an oxysilyl column that's approximately 1 meter in length and 50 microns in diameter. A charge is applied across the column, and compounds within the injected sample separate based on their charge and ionic radius. Metabolites with a small ionic radius exit the column first, and metabolites with a larger ionic radius have a longer migration time. Because compounds analyzed in the CEMS are separated based on ionic radii rather than polarity, CE, in many scenarios, outperforms LC and GC separation methods, as highlighted in the case of the separation of structural isomers glucose 1-phosphate, fructose 6-phosphate, and glucose 6-phosphate. It's likely that conventional methods will detect these isomers under one peak. However, with CE, isomers can be separated cleanly, which leads to the accurate quantitation of a greater number of metabolites. CEMS is especially good at capturing charged and hydrophilic metabolites, as highlighted in the case of nucleotides. It was shown that better separation and detection was achieved by CEMS when compared to LCMS. Traditional metabolic profiling experiments most commonly employ liquid chromatography or gas chromatography as methods of analyses. LC and GC are well suited for analyzing neutral and volatile compounds. However, the vast majority of compounds involved in primary metabolism are charged and therefore difficult to capture by LC or GC. Additionally, using HMT's capillary electrophoresis tandem mass spec method, the quantitation of anionic metabolites found in the nanomolar and subnanomolar concentration range in biological samples can be achieved. In addition to analyzing human biofluids, tissues, and cultured cells, HMT has 10 years of experience profiling the metabolome in microorganisms, plants, and foodstuff, and provides results for over 300 commissioned projects each year. In the case of urine and blood, the recommended sample requirement for analysis is 100 microliters. In tissue and plants, 30 to 50 micrograms. 2 million cells for cultured cells, and in the case of microbes, 10 to the 9th cells. It should be noted that these requirements are general guidelines to ensure that all of the metabolites in the sample exceed the detection threshold. In the case of cultured cells and media, sample pretreatment is performed by the customer prior to shipment to HMT America using a standard metabolite extraction protocol and kit containing filter tubes and internal standard solution provided by HMT. Blood and tissue samples are simply frozen and shipped directly to HMT America. Samples are then analyzed in Japan, and a comprehensive report is provided, at which time our customers can easily export the results and figures to a publication, patent, or presentation. HMT scientists are available throughout the entire process, and also for a post-analysis meeting to discuss results and data interpretation. HMT's Global Analysis Service Package Basic Scan provides the relative quantitation of peaks annotated from an internal library of over 900 standard metabolites. A comprehensive report with multivariate statistical analysis and pathway map are provided. This untargeted analysis package is most suitable for biomarker discovery. HMT has 10 years of experience developing pipelines for central nervous, renal, hepatic, and gastroenteric diseases. HMT's biomarkers for major depression and diabetic nephropathy have made it to the late stages in the development pipeline. HMT's commissioned biomarker discovery services are currently performed under GLP-compliant conditions. HMT's most promising biomarker, ethanolamine phosphate, is measured in the plasma and can identify patients suffering from major depressive disorder. What makes this biomarker unique is that it can distinguish patients with MDD from patients suffering from other mood disorders such as adjustment disorder. HMT has recently developed Carcinoscope, a targeted metabolome analysis package specifically designed for cancer research, and provides the absolute quantitation of 116 cancer-relevant metabolites and 30 metabolic parameters involved in primary metabolism. Multivariate statistical analysis, including HCA and PCA, are reported as heat maps and score plots, and a comprehensive report with metabolic pathway map that can be exported to a presentation, publication, or patent application is provided. The influence of energy metabolism on cell survival and proliferation is considered to be a hallmark of cancer that is often investigated with the purpose to develop new therapeutics and biomarkers. Carcinoscope profiles 116 metabolites found in cancer-relevant pathways, including glycolysis, pentose phosphate pathway, TCA cycle, urea cycle, and purine, polyamine, and amino acid metabolism, thus capturing the metabolites most closely associated with the hallmarks of cancer. Please contact us for more information and pricing, and thank you for your kind attention.